This lecture is going to be an introduction to polar coordinates as well as doing some calculus with polar coordinates. First off, what is a polar coordinate? It's a different way of writing a point in the plane. Instead of going x over and y up, we talk about the angle of this ray that we're going to tilt up, and then how far along this ray will our point be. Now, one problem with this, or not a problem, something that's interesting, is there's more than one way to describe this point. I can say, this looks like it's about 60 degrees. No, it looks more like 40. So I've got 40 degrees, and this is maybe 2, so 42. So I could also get to that point by going around a whole circle and then do theta. So that's another way of describing that point. I could come from the other direction. I could say negative and go this direction and still get to the same point. I could even use a negative radius and say my angle is theta plus pi, but I want to go negative r, which is also going to put me on p. In fact, you could go really crazy and do lots and lots and lots and lots of spins before you get there. So there's infinitely many ways to describe any one point, though we tend to stick to the ones where the angles are normal, between 0 and 360 or 0 and 2 pi. So what can we do with this? Well, we want to be able to go back and forth between the two. We know from doing that trig unit circle thing that x is r cosine theta and y is r sine theta. To go the other way, r is the radius, so it's the square root of x squared plus y squared, and theta is the arctan of y over x. So let's do a couple of conversions. Suppose I want to take the point 3 pi over 6 that's polar and change it to Cartesian. Well, x is r cosine theta. So I fill in what I know and simplify. Y is r sine theta, crank it out. And I get 3 square root of 3 over 2, comma, 3 halves. Now let's go the other direction. This gets a little trickier. So I'm going to go ahead and plot the point. Make sure we know where this is. This is negative 5, 4, so we're over here in the second quadrant. So my radius is the square root of x squared plus y squared, square root of 41. Easy peasy. My theta is arctan of negative 4/5, which is negative 0.6747, yada yada. You can read it. Now the problem with this is if my angle is negative, that means I'm going to be in this quadrant. But I know I'm supposed to be in this quadrant. This is that weird thing that happens when you do arctan. To force arctan to be a function, it will only crank out numbers or spit out numbers between negative pi over 2 and pi over 2. You need to be able to massage it and put it where it's supposed to be. So in actuality, I don't want negative 0.67. I want pi minus 0.67. Or even I want to go negative 0.67, but my radius is negative. So there's two ways. Well, like I said, there's infinitely many ways. But you need to be able to take this and say, okay, that's not the answer. I need to play with this some. So my real, because that's where that's plotted. I keep forgetting that's coming up here. That's where that was plotted. So I want it over here. So I have 4 square root of 41 and pi minus that hideous number gives us 2.46 blah blah blah. Or we can make our radius negative. So now that we know how to plot points in polar coordinates, and we can go back and forth between polar and Cartesian, let's look at graphing some equations in polar equations. So polar equations are going to be of the form r equals f of theta, typically. And the first graphs I want to look at, or equations I want to look at, are the constant equations. If r equals 2, that means all the radii are 2, so it's a circle with radius of 2 centered at 0, 0. If I say theta equals 1, as in 1 radian, which is about 59 degrees, we're going to have the ray where the radiuses can be positive or negative, but the angle is always going to be 1. So that gives us a line. Another interesting thing is when you look at something y equals theta, then you get this pretty spiral. I like the spiral. Okay, now let's look at some more likely equations that you play with. You tend to do the trig equations when you do polar equations. So let's start with cosine of theta. So just like when you first started graphing, way back when we started plotting points, we're going to plot points here. So I'm going to look at, this is basically every 15 degrees, and it's only in the first quadrant. Here's the cosine of those values, and I'm going to plot the points, and I get yada yada. I get that. Now, when I go into, and this is only plotting the first quadrant, I said that. In the second quadrant, all my values are negative, so even though my angle is going to be, 7 pi over 12, my radius is negative, so I'm going to be down here. So there's my negative radii. Those are all my angles in the second quadrant. When I plot those points, I get the dots on the bottom side. So r equals cosine theta, we get a circle that's centered off on the side there. Now let's do the same thing with sine. Too far, too fast. R equals sine theta, we again get a circle, but this time the circle is centered on top. Centered on top? It's on top of the origin. Look at it, you know what I mean. Now, how can we mess with these equations? So we get a circle for sine and cosine. What if I multiply it by 2? Well, that means all your radius are twice as big. So you get the same circle. 0 times 2 is still 0. But now my circle has a radius of 2 instead of a radius of 1. And actually, that's not a radius of 1. That's a radius of 1/2. Okay. But it's twice as big. Now, another thing I could do is put a 2 here and say sine of 2 theta. Now what that does, remember, is it changes the period. Your r is going to go up and down twice as fast. And so as you go around the angles, instead of taking its time to go out and back in, it's going to go out and in and out and in. So we get this pretty flower. What else can we do? Well, we can add to it. Let's look at sine plus 1. Now keep in mind, sine is normally between -1 and 1. By adding 1, we now have something that's between 0 and 2. So we get this kind of funky, what they call cardioid. It's supposed to be a heart, but hey, I'm thinking heart should be pointy up here, but it's not. So plus 1, we're all positive. I could add 2 to it, and then it's really cattywampus. It looks kind of funky. Now, if you add a half or anything between 0 and 1, or subtract anything between 0 and 1, that means some of your lengths are positive and some of them are negative, so you end up with this little loopy thing in the middle, which is kind of cute. So that is that's an introduction into polar equations. I'm going to actually do the calculus in a separate video, so it's not so much at once. So I am ending this one here.